Hi, my name is Michael Hawes. I'm doing my presentation on reconstructing the Higgs boson invariant mass from simulated collider data. Again, my name is Michael Dean Hawes. Uh, what we attempted to do in this project was to recreate and resimulate how they discovered the Higgs boson. Um, so uh, in this project, what they did was um, so CERN has a data table set you can go onto, and you can pull out a bunch of data sets, and they have one for the 1998 data sets, meaning that there was 1,998 simulated uh, events that led to the discovering of the Higgs boson. And so this is a chance or to attempt to recreate that finding. So, to start off, we have several different scientists here. We have Peter Higgs, Francis Englert, Robert Brout, Gerald Gerlink, Carl Hagen, and Tom Kibble. There was more, and that obviously went into help finding and predicting the Higgs boson, but these are some of the few that were very instrumental. All right, so this is Peter Higgs. So he's at a chalkboard, and he looks like he's. I'm not sure if this is just a computer-generated uh, picture of him, but Peter Higgs was notably the one who they named the Higgs boson after, because he was instrumental to finding or predicting this particle. And this was over in the 1960s. So the Higgs boson was actually uh, rediscovered or was discovered in 2012. So this was over 52 or 48 years later. Okay, so you're probably wondering, why is the Higgs boson important? So the Higgs is important because it answers the questions of why do particles have mass? Particles like the electron, the bosons, the quarks, all of these in the other standard model, the previous standard model, uh, they were massless. Everything was massless, which gave beautiful math, beautiful symmetry, but they felt was physically wrong. And so that was kind of the things that scientists wanted to tackle was having a more physically accurate uh, standard model. And the Higgs boson helps support these findings. So what is the Higgs? So there's kind of two parts. There's the Higgs field, which is a field where a lot of these particles, like the like the bosons and the quarks and the electrons, can interact with this field, and their mass changes, which is very interesting. The field it exists everywhere in the universe, and and yeah, and it's there to kind of show that there is a way for these particles to have more mass. Okay, so you might be wondering, why don't they have set masses like atoms? Um, so atoms are built up of very foundational building blocks. Things like neutrons, protons, um, but those protons and neutrons are created of even smaller particles. And at this level, it gets very hard to observe and detect these particles because they're just so small. And so a lot of this is built based off of math and simulations and lots of experiments. But they have felt like they can confidently say that these, subatomic particles are real. So these particles, such as quarks and electrons, um, so they are uh, so they came up with a theory called the Yukawa coupling. Basically, a strength setting between a particle and a field. And so they're noticing at this level that they're getting so small that they're behaving at more of this duality, this particle wave duality, which is really interesting. So what are Yukawa couplings? The Yukawa couplings are the strength of interactions between a fundamental particle and a Higgs field. So each fermion or quark or lepton, these are subatomic particles that they find all the time in particle accelerators. Um, so they have their own couplings, their own constant controls and how much mass each particle gets. The stronger the coupling and more it drags in the Higgs field, the heavier the particle. So things like electrons, they have a very weak uh, coupling. Uh, so when they go through the Higgs field, I think they might not get as heavy as say maybe a top quark, and they don't understand why that is. But top quarks become very heavy when they interact with this field. So how was the Higgs discovered? So a Higgs boson decays in less than a zeptosecond, which is 10 to the negative 21 seconds. The scientists never see it directly, but instead they search for it. As they search for it, it decays, and particles. It decays into other particles, and that's kind of what they're looking at is this aftermath of many different particles. Um, so what a channel is a way in which unstable particles decay into other particles. So we'll take a look at channels real quick. So in a particle accelerator, what they do is they take particles and they speed them up, to 99.99999, I don't know, very, very quickly, very almost near to the speed of light, very close to. So this channel, so this Higgs boson is a YY, which is 2 photons. So this Higgs boson is decaying into 2 photons, or this Higgs boson is decaying into Z bosons, 4 leptons, or 2 W bosons and 2 leptons, and plus neutrinos. So 2 bottom quarks, 2 tau leptons. So they decay into a lot of different particles. So how was it predicted? So I guess that's kind of, we should probably go back a step and say, how was this predicted? So in 1964, as a new theoretical mechanism that could explain how particles acquire mass, known as spontaneous symmetry, breaking this mechanism allowed massive W and Z bosons to exist in a theory that was originally only valid for massless particles. Physicists including Peter Higgs, Francois Englert, Robert Baruth, Gerald Guralnick, Carl Hagen, Tom Kibble. So they proposed that a universal field, now called the Higgs field, fills all space when particles interact with this field. They gain mass. The Higgs boson is the quantum explanation of this field and its discovery in 2012, and confirmed the mechanism that gives mass to fundamental particles. So my simulated project was based off of this experiment. Okay, so I'm not sure if I already said this. So in this project, we are here to recreate and reconstruct this experiment using Python. And then we're going to try to detect on a histogram a peak near 102.5 GeV. So, so the invariant mass is calculated using energy and momentum conservation. So electrons and momentum. This formula reconstructs the mass of the original particle using its decay products. So mass peak in the histogram shows common origin, confirming the particle's presence. So m is equal to, these, yeah, this energy and these momentum. So, um, so here's the histogram. So this is the Gaussian curve. This is the red line shows us Gaussian fit, and the true Higgs mass uh, is at 102.5, and you can see that green line right there. And then the blue is obviously the simulated data. So what about these results is that in the histogram showed a peak near the expected Higgs mass at 102.5 GeV over 1998 total decayed Higgs events. Despite the randomness and uncertainty, the Higgs kept showing a bump at 102.5 GeV, which is what scientists were looking for. The conclusion research has spent billions of dollars on research and physics instruments. You know, physics is one of the most expensive, I think, fields because everything when you're trying to produce something like fusion or these colliders, you're in a field that is extremely expensive. Um, but it's still very important to uncover these things. Um, so to think about the physics is so expensive. So probably the most expensive thing, yes, ever, which is physics. So it sounds like they had to produce something, and after millions of data sets later, they conclude that a new particle that was predicted decades earlier, um, they counseled and concluded, and they talked about among themselves, and they had lots and lots and lots of evidence to suggest that this particle is indeed real. Um, and it in 2012 it altered our standard model, and we'll see. I don't want to just say forever because everything changes in science. Everything's waiting to be understood more fully and clearly, and so uh, you know. So for now, we have the Higgs boson as part of our standard model for particles uh, in that level, and which is great.